Hi, I'm Prof and welcome to Chemistry Matters. And today we are going to be talking about titrations. The very word titrations might spark fear and loathing in some of you, possibly, who have been subjected to these at school or at university. But they are extraordinarily useful in determining the concentrations of solutions of unknown concentration, okay? The way that a titration works is essentially you take a solution of known concentration and you utilize a stoichiometric reaction between that and a solution of unknown concentration to figure out the unknown concentration. That's essentially the guts of a titration. The way that you carry out titrations, you normally have one of your solutions in a burette, like this. You have the other solution in generally a conical flask, and you add slowly the solution from the burette into the conical flask until an indicator in the conical flask changes generally color, okay? And that's what we call the end point of our titration. That's when we know that the reaction has gone to completion, and we can then do our stoichiometric calculations and figure out what the concentration of the unknown solution is. Now, this, as I say, is very useful for determining essentially the concentration of any type of aqueous solution, but we are going to concentrate today on acid-base titrations. So in other words, we're going to be using titrations to determine the concentration of an unknown acid solution or an unknown base solution. Okay, so let's have a look at how the pH changes as we carry out an acid-base titration. So there's 4 possible acid-base titrations that you can do, and so we're going to look at how the pH varies during these for all of these 4 different types of titration that we can have. We're going to start off with a titration of a strong acid, which is going to be sitting in our Erlenmeyer flask, in our conical flask, and we are going to be titrating that with a strong base. So we could imagine sodium hydroxide being in the burette, and we could imagine HCl being in our conical flask. And if we had a pH meter sitting in our conical flask and we monitor the change in pH as we add the sodium hydroxide, we would get a curve that looks very, very much like this, okay? So we would start off at a pH of around about 0.7 because we're using 0.2 molar HCl. So the pH of a 0.2 molar HCl solution is around about 0.7. And we're going to start adding to that sodium hydroxide. So open the tap on the burette, away you go, swirl, 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 and monitor your pH. And you'll see that the pH is not changing very much along here at all, okay? Now, we've got 25 mils of 0.2 molar HCl. We're titrating it with 0.2 molar sodium hydroxide. We know that if we wrote the balanced chemical equation for that reaction, it would be a 1-to-1 reaction between HCl and sodium hydroxide. So we would expect the reaction to be all over when we've added exactly 25 mils of sodium hydroxide to our 25 mils of the HCl. So here we go. The pH is not changing very much. It's pretty flat all the way along there until we start getting close to 25, and then, wow, the pH changes enormously within even 1 drop of sodium hydroxide from our burette. We get a massive change in pH from around about 2 and a bit to what, about 11, something up there, within 1 drop. Okay, that's 9 orders of magnitude change in the H3O plus concentration. So you get a massive change, and then you go out here and the pH again doesn't change very much at all. Okay, so what are the important points in our pH curve here? Well, one very important point here is the equivalence point. So the equivalence point of any titration is the point where the reaction stoichiometry is satisfied. Whatever that means. In other words, it's when the reaction has finished. When you've added exactly the same number of moles of your base as you had number of moles of your acid to start off with. Okay, now when you're doing a strong acid, strong base titration, you'll always find that the equivalence point has a pH of exactly 7. Okay? The reason for that is that when we have added exactly the same number of moles of sodium hydroxide as we have HCl, what have we got in our solution? Quite simply, we've got sodium chloride, NaCl. Okay? And sodium chloride is an extraordinarily weak base. Okay, so that doesn't do anything to the pH. That's going to have a pH of 7. So we call this region here the acidic region because obviously the pH as we go all the way up to 25 mils is on the acidic side of 7. We call this the alkaline region or the basic region. Okay, again, after you hit your equivalence point, the pH is greater than 7. And one other thing to notice here, look at that, the pH doesn't change very much, and you're adding quite a lot of sodium hydroxide. The pH is not changing very much. Some of you might think, that's a buffer solution, because the pH is not changing very much when we're adding a strong base, okay? Now, yep, that looks at first glance like it might be correct, but there's also another part to the definition of a buffer solution, okay? And a buffer solution has to resist change in pH on reasonable dilution, okay? Now in this case, if you dilute the solution here by tenfold, the pH will change by 1 order of magnitude. It doesn't resist change in pH on reasonable dilution, so that in fact is not a buffer solution in there. Okay, that's strong acid, strong base. We can then fairly whiz through the strong base, strong acid titration because it's essentially a mirror image of the strong acid, strong base titration. We start off with 0.2 molar sodium hydroxide up here. In our conical flask, we're going to add now 0.2 molar HCl from the burette, and that's going to give us now a titration curve that looks like this. The equivalence point again, the pH at the equivalence point is going to be 7 because of the fact that, again, at the equivalence point, you've got a solution of sodium chloride, NaCl. You again take exactly 25 mils to get to the equivalence point. That's where the reaction is essentially all over. And any acid that you keep adding to the solution after that isn't doing anything. Okay, it's not reacting, it's just sitting there changing the pH, albeit relatively slowly. Okay, so strong acid, strong base, strong acid, pretty straightforward. Here we go now, weak acid, strong base titration. And you can see pretty immediately that there are some differences, okay? For starters, we're not starting at such a low pH because now we've got a weak acid, 0.2 molar acetic acid. So we start at a pH around about 2.7-ish, there or thereabouts. We get a little bit of a curve here, and then again, as we approach 25 mils, a sudden change in pH which is not as great. And then again, in the alkaline region, relatively small change in pH because all we're doing is adding excess sodium hydroxide. Okay, now the big difference here is the pH at the equivalence point. pH at the equivalence point of this titration now is on the basic side of 7. It's 8.88. Okay, why is that? Well, think of what we've got in solution when we're at the equivalence point. We've added sodium hydroxide to acetic acid, and we've added one equivalent of sodium hydroxide to acetic acid. So what we have there is the acetate ion, don't we? Okay, we've got a solution now of acetate ion. What do we know about acetate ion? We know it is the conjugate base of a weak acid. So therefore, it is a weak base, isn't it? And it can therefore react with water to give us the undissociated acid plus OH minus. So acetate ion, a weak base in solution, you are going to get production now of OH minus in that solution. If you do the calculations, and the calculation is nothing more than just the pH of a solution of sodium acetate, and you know how to do that hopefully looking back on some other videos, you will find the pH of 8.88 due to the production of OH minus from that. Okay? So that is a very important facet of the weak acid, strong base titration curve. Okay? So acetic acid and sodium hydroxide. The last one that we're going to talk about is the weak base strong acid titration, and again, mirror image of the previous. So in this case, you're starting off at quite a high pH, but not as high as the strong base strong acid, so around about pH 11 or so. And in this case, we're titrating ammonia, 0.2 molar ammonia with HCl of the same concentration. Again, you're getting a relatively shallow curve here, a decent sized change in pH as you get to the equivalence point, and then dropping off and not changing very much. Again, the volume that you need to get to the equivalence point is 25 mils. And at the equivalence point, again, you can see a big difference here. Now we're not pH 7 anymore, we're pH 5.12, okay? pH of 5.12, we're on the acidic side now of 7. And the reason for that is, again, we think about what we have in solution at the equivalence point. We have added exactly 1 mole of HCl to 1 mole of NH3. So what do we have? We have got a solution essentially of, or certainly containing, NH4 plus. In fact, it's a solution of ammonium chloride. We'll leave the chloride out of it just for convenience. Ammonium ion, NH4 plus. Now that is the conjugate acid of a weak base. Because it's the conjugate acid of a weak base, that makes it a weak acid. And a weak acid can react with water to give the free base plus H3O plus, a little bit of hydronium ion, okay? And that little bit of hydronium ion then pushes the pH to below pH 7. And so that, again, is a defining characteristic of the titration of a weak base with a strong acid, okay? Weak base, strong acid, we're going to have an acidic equivalence point. Weak acid, strong base, we're going to have a basic equivalence point. And with the strong acid, strong base titrations, either of those strong acid, strong base, strong acid, you're going to have a pH at the equivalence point of exactly 7. Okay, so let's then finish this up by doing a very quick calculation just to show the pH at the equivalence point in this titration here, where we are titrating 0.2 mole per litre ammonia with 0.2 mole per litre HCl. So let's just show that this does in fact work, okay? So, as we said, if we're titrating ammonia with HCl, at the equivalence point, we have got a solution of ammonium ion, and that can react with water to give us NH3 plus H3O plus, okay? And we can write a Ka expression for that. It's going to be NH3 multiplied by H3O plus concentration over NH4 plus concentration, okay? Now, because we started off with a 0.2 molar solution of ammonia and a 0.2 molar solution of HCl, then the final solution, the concentration of our ammonium ion now is going to be 0.1 mole per litre, okay? So essentially what we have is a 0.1 mole per litre solution of ammonium ion, okay? That's the initial concentration. So therefore, we could do a calculation now involving a concentration table, okay, which we've done in previous examples, previous videos. We're not going to go through and do that. We're just going to do the quick and dirty method here. We're going to use the equation that, again, we have used in a previous video, we know that the H3O plus concentration is equal to the square root of Ka multiplied by the initial concentration of the weak acid, okay? That means that we need to know the Ka of ammonium ion, and the Ka of ammonium ion, again, this would be given to you, is 5.5 times 10 to the power of minus 10, okay? So then knowing that the H3O plus concentration is the square root of 5.5 times 10 to the minus 10 times 0.1, and that comes out at 7.42 times 10 to the negative 6 mole per litre, per litre, and then we take the negative log of that, and the pH that we get is 5.13, which differs from 5.12 just a little bit through some rounding that we were doing. But again, you look in the book, the pH at the equivalence point, 5.12, we've calculated 5.13, that's pretty good. Okay, so all that this calculation is the pH of a solution of a weak acid. And entirely analogously, we could do the pH of a solution of a weak base if we were looking to find the equivalence point of the weak base strong acid titration. Okay, but again, as I keep stressing here, most of this is stoichiometry. Most of this is playing around with balanced chemical equations and then utilizing an equation or two to get your pH. Okay, so nothing too scary there, I hope. But again, a rather in-depth look, I guess, at the important characteristics of all of the possible titration curves. Okay, so that'll do from me, and we will see you in the next video.